Welcome back, friends. So we have been looking at the wave functions of the Dirac equation. Okay, we have been looking at the wave functions of the Dirac equation, and I kept saying that this is not a scalar wave function, but it's a spinor, and I called it as a Dirac spinor essentially because it has 4 components. It is looks like a vector, but it's not a vector. Okay, and I told you it's not a Lorentz vector. Then what it is? So what is it? I wanted to tell you in a more mathematical sense that these are representations of in sense of Clifford algebra, but in other words we can also think in terms of these things to be vectors of unitary group. Essentially these are fundamental representations of unitary groups. Now this looks like a big word essentially. We didn't do a little bit of any bit of group theory, but so to start doing group theory we won't do the full group theory, but we will do the group theory which is required for us essentially. Now before going further I wanted to mention that the number of dimensions of this spinor are dependent on number of alpha and beta matrices which we require to satisfy this E is equal to P plus alpha I pi plus beta m. So this is the number of alpha matrices which are linearly independent alpha matrices which we require. Now this will depend upon number of dimensions you are in essentially, and we looked at several examples of it essentially saying that if you have say something like 6 dimension space time essentially hypothetical, essentially these are all you need spinors of dimension 8, and if you are looking at 1 plus 1 dimension, so imagine that you are only confined to a plane essentially. Okay, in that case you only need 2 sigma matrices or gamma matrices. So the gamma matrices reduced to 2 dimensions essentially, and the spinors would be just left movers and right movers essentially. Okay, so after saying this then we started proceeding towards group theory. To understand a little bit of group theory, we won't do a full lecture course on group theory because it's a huge topic. So what we are going to do is only parts of the group theory which are interesting for us essentially. The kind of groups which we are interested are essentially something called continuous groups, and what is the relation between the Dirac wave functions which are spinors and the Lorentz group. Okay, and why does Dirac wave function come out as spinors essentially, the wave functions come out as spinors. That is the issue we want to address essentially. So then we looked at groups essentially. Generally groups are sets of which satisfy the axioms of closure, associativity, identity and inverse. Okay, and now this is a collection of objects. Now groups can be either discrete or continuous. So what we are interested in is continuous groups essentially. So the continuous groups of the type which can be slowly modified from infinity from unity essentially, not infinity, unity. So we looked at the rotation group in 2 dimensions. So why it is a group? Because you do one rotation and then do another small rotation, next rotation, together it forms some group where it also belongs to it also belongs to the these 2 rotations also belongs to the the rotation group itself, the group element essentially. This transformation also belongs to the group itself. Say for example g of theta and g of theta plus theta is equivalent to g of theta prime, where theta prime is nothing but theta plus delta theta. Okay, theta prime is nothing but theta plus delta theta. So this is consistent essentially that a group action of theta and a group action of theta plus delta theta is equivalent to a group action of theta plus delta theta plus theta essentially. Okay, so it is 2 theta plus theta. Anyway, so okay, maybe it's much easier to write it in simplest sense. So let me write it as, so that instead of introducing so many notations, theta prime, theta plus theta prime. So this is the group action. That means that if you rotate it with one angle theta and next you rotate it with another angle theta prime, this is equivalent to a rotation of an angle of theta plus theta prime. So this is the basic idea of group. And if you have discrete groups, these are essentially things like reflections, crystal groups, permutation groups, so on. So essentially, whereas if you have continuous groups, they are essentially the most important example of the continuous group is something called the rotation group. There are various other possibilities which you can consider, but rotation groups are some things which we are interested in. And now what do these continuous rotation group do? It keeps the length of the vector in 2 dimensions, meaning invariant. So from that you can derive that this group is an orthogonal group. So that means OO transpose is equal to 1, which we said essentially, and so this is an orthogonal group. And how many elements, free elements the orthogonal group contains? This is where our discussion was. Essentially we said that this is an orthogonal group. And now let's look at what are orthogonal groups in detail, and then we'll also look at dimension 3 orthogonal groups where we stopped our discussion last time essentially. Okay, what are orthogonal groups? Orthogonal groups are represented by matrices which are orthogonal to each other. Okay, so that means if there is a group G, or which we call it as an orthogonal group, so let me call it as SO2, or orthogonal groups are ON. ON, we can also call it as ON. We'll see the notation a little bit later, what S stands for, what O stands for, and everything. So let me just for the present, without introducing S, let me call it as O2, ON for n general dimension essentially. Okay, then O transpose O is equal to 1. Okay, O transpose O is equal to 1. Now why this happens? Because this is exactly what we had. We call it as R essentially. R transpose R. R is a rotation matrix, right? Essentially R transpose R. We got this condition that R transpose R should be equivalent to 1. Only then the length of the vector is always invariant under rotations. Okay, so this is called an orthogonal group. This just tells me that it's orthogonal. Now if you take so this is same as R transpose R is equal to 1 as introduced earlier. Now let's take a 2-dimensional matrix O. Let me call it as a O, B, A, B, C, D. It is made up of 4 elements essentially. It's a 2-dimensional matrix. And then I impose the condition O transpose is equal to 1, 0, 0, 1. This should be 1. Now why I impose this condition is because what this condition implies in the number of free parameters in describing this orthogonal group. So now I define O transpose is equal to A, B, C, D. O transpose would be A, C, B, D times A, B, C, D. It is instructed to do this exercise once essentially because it makes our understanding clear. So, this means this is equivalent to A square plus C square AB plus CD BA plus CD B square plus D square. So, the conditions are this should be equivalent to 1 0 0 1. Okay. Okay. Now, you can equate each of them. So, how many elements you started with? The number of free parameters was equal to 4 A, B, C, D. Okay. And assuming A, B, C, D are real. Now, number of conditions from this equality is 3 because this and this give you the same condition A, B, C, D plus A. Okay. So, you have A square plus C square is equal to 0, the first condition, and then AB plus CD is equal to AB plus CD is equivalent to 0. So, there is only one condition, and finally one independent condition, and finally you have the third condition B square plus D square is equal to 1. Sorry, this should be 1. Okay. So, these are the conditions. So, number of conditions is equal to 3. So, number of parameters is equal to 4. So, if you solve them, so number of free parameters is equal to 4 minus 3, that is equal to 1. In fact, as you will see, one of the exercises would be that how to I think this will be based on one of the questions which will be asked in your exams, essentially that number of free parameters, this can be generalized to n dimensions. Okay. Okay, let me come to n dimensions once, because number of free what is this number 1? So, what is this parameter? This parameter is nothing but theta. Okay, this is an orthogonal group. So, you have this theta. So, that is the reason you can only have one free parameter, which is the reason why cos theta sin theta minus sin theta cos theta. So, this is called O2. Now, what is SO2? I wrote as SO2 earlier. Essentially, SO2 is special orthogonal group such that the determinant of O is equal to plus 1. So, in an orthogonal group, the determinant can be both plus and minus 1. Okay. And in the case of so both are possible. Now, how do you see this? Because you see it from the same relation essentially. Det of, if you take O transpose O is equal to det of 1. So, that means det O whole square is equal to det 1. So, which is equal to 1. So, this means det of O is equal to plus minus 1. Now, this condition will not give you anything new. Okay. It will not reduce the number of parameters essentially. Okay. In special orthogonal, we will see a case in which it will reduce the number of parameters when ABCD becomes complex. When ABCD becomes complex, the number of parameters will reduce. So, ON and SON will have the same number of parameters, free parameters essentially, which will describe the group elements essentially in general. Now ON and SON will have same number of parameters to describe the group elements. The group elements are nothing but rotations here essentially. Okay, in this case they are nothing but your rotations essentially. Now let us look at the next case essentially, what happens for n is equal to 3. Okay, and also tell you what happens for n is in general n. I will give you the formula, but you have to derive it as a homework. For general n, okay, meaning for n dimensions essentially, the formula, can you derive this formula actually? Okay, you can derive this formula, and you will get n into n minus 1 by 2 free parameters essentially. Okay, so for a general n square parameters, okay, now you also have n into n plus 1 by 2 conditions. Why? Because n into n plus 1 conditions, because only the orthogonal meaning the upper diagonal part. Okay, let us take, okay, so O dimension transpose O, this is one matrix and this is matrix. The number of conditions on the upper direction are only useful, because the lower direction conditions essentially are equivalent to 1, say for example 1 1 0 0 1. Now these conditions replicate in the bottom direction. These conditions on the top are the only independent conditions. The lower dimensional conditions are the same essentially as the top ones, so they won't give you a new set of conditions. So that is the reason why you have n square parameters for a general matrix. Okay, and n into n plus 1 are the upper triangular matrix conditions, essentially n is equal to n square minus 1. So the number of free parameters is equal to n square minus n into n plus 1 by 2, and that is equal to n into n minus 1 by 2. So an n dimensional orthogonal matrix will have n into n minus 1 by 2 free parameters. So the number of free parameters for n dimensional orthogonal orthogonal matrix. Okay, good. So now for n is equal to 2, I said that matrix is abelian. Okay, the matrix is abelian, group is abelian. Okay, in the sense that if you rotate it first by theta and then by theta prime, the product is theta plus theta prime. Now this does not matter if the order of rotation is changed essentially, if you if it's because only there is x and y. Okay. Now if you rotate it the other way around also, So if you start rotating with theta prime first, which is smaller angle, and then with theta, which is the bigger angle, then these rotations are identical. So you will get again theta plus theta prime. Rotation essentially. So you can interchange rotation, interchange. So okay, you can interchange rotation of theta, rotation by theta prime is equal to rotation by theta prime plus rotation plus theta. So this group is abelian. So that means that you can interchange the operations essentially. So you can first multiply by theta prime or what I mean what in whatever order, the final result is the same essentially. But if you go to 3 dimensions, okay, if you go to 3 dimensions, for n is equal to 3, the number of parameters free parameters describing the orthogonal matrix orthogonal matrix or orthogonal group is this now group is called O3 group. Okay, O3 group would have 3 square 3 into 3 into 3 minus 1 by 2, that is equal to 3. Okay, so they will have 3 free parameters essentially describing your any orthogonal matrix in 3 dimensions essentially. Now any orthogonal matrix in 3 dimensions are nothing but your 3 angles for rotations. Rotations in 3 dimensions. So 3 angles for rotations in 3 dimensions. So if you have 3-dimensional thing plane, okay, let me see if I can draw it essentially very I am not sure. Okay, if we can, you have a vector, so you can have phi, an angle, another angle would be theta. So there could be a rotation between these two, there could be a rotation with these two essentially. So you can have 3 angles essentially between x, y and z. Okay, so there are 3 different angles essentially. These are your 3 Euler angles of classical mechanics, or you have rotations in r, you have rotations in psi, and you have rotations in phi. So this is the same thing which I introduced last time as rxy, rzx and rzx essentially. Okay, these are your 3 angles in the xy plane, yz plane and zx plane. Now then I also introduce, okay, so these are your 3 angles essentially. Now the point is that if you now this, so a general SO3 element, SO3 or O3 group element is a product of some r theta, r psi and r phi, but the order matters. Okay, but the order matters. What I mean by it, that the element r theta, let us say r theta is xy plane, yz plane, zx plane, r psi, r phi This is also group element. This is one group element, but this group element is not equivalent to this group element, where I interchanged psi and phi. Okay, so I interchanged psi and phi. Okay, so if you interchange some the order of multiplication, this is not the same group element essentially, and such groups are called non-abelian groups. So these are called non-abelian groups. Okay, these are called non-abelian groups. Now this can be understood clearly why it happens. So essentially, now suppose if you won't come, and the point is that you take the vector r. Okay, horrible. This is not neatly written. Okay, so let's just say let's take this vector r. Okay, now let me rotate. And the point is that if these are equal, the vector should come back to it the same point after rotation of theta, psi and phi, say for example. So suppose if I rotate it by theta, then I rotate it by psi, and then I rotate it to by phi, so it will come to some other point, say for example at this point. Okay, the length of the vector doesn't change, but because rotations don't change the length of the vector, as we have seen, this is true. But now when we interchange the rotation, say for example it still rotates to r theta, but then it goes to first phi and then go to psi, so it will end up being at a completely different point, essentially at say here. So the point is this rotation, which is given by blue, okay, and this rotation which is given by red are not the same. So the point is in 3 dimensions, because you are rotating over 3 different angles essentially. So the order of rotation matters. The order of rotation matters, and that is the reason while these groups are orthogonal groups, and the moment you go more than 2 dimensions, so for 2 dimensions you only have one angle, for 3 dimensions you have 3 angles, and so things become complicated, and these become known as non-abelian groups. Okay, these become known as non-abelian groups, and in general orthogonal groups and the complex counterpart of them called unitary groups form something called the Lie groups, which I have introduced something. These are called part of Lie groups. Okay, now what are the generators of this for infinitesimal transformations essentially? Now let us write down explicitly r theta. R theta would be in 3 dimensions cos theta, sin theta, minus sin theta, cos theta, 0, 1, 0, 0. Okay, then r's. Now because cos theta I define to be in x and y plane, so it will be an angle of rotation in x and y plane, and cos psi I define it to be in y and z plane. Okay, y and z plane, so this will be of the form psi, sin psi minus sin psi. And finally the third thing, okay, y and z is psi, and z and x would be phi, so which is r phi cos phi sin phi 0, 1, 0, 0 minus sin phi 0 cos phi. Okay, now we can introduce, now that we have defined these 3 generators, these 3 matrices in which are the most general form of these matrices. So any general matrix would be a product of these three, but before doing while it is true, we can express them in much more simple language by introducing the language of generators. Infinitesimal rotations which are given by x of theta is equal to minus dou r by dou theta, theta goes to 0 essentially. So, okay, we will define a minus sign. So, this is given by r theta x y is equal to 0, 1, minus 1, 0, 0, 0, 0, 0, 0. So, what does this x do? X generates tiny infinitesimal rotations essentially, okay, tiny infinitesimal rotations. Now, if you multiply with delta theta, it gives you one rotation. So, this is a rotation in xy plane essentially, x and y plane. Okay. Similarly, you can rotate define for psi, this will end up being 0, 0, 0, 0, 0, 0, 1, minus 1, 0, and x of this is in yz plane and this is xz plane essentially, this is equal to theta of phi, this is equal to 0, 0, 1, 0, 0, 0, minus 1, 0, 0. So, these three are your generators of infinitesimal rotations. So, I will stop here and then we will continue our class essentially on understanding the rotation group in detail and what this has in the connection with the Lorentz transformations and how the spinors will end up having being the representations of the Lorentz group essentially. Okay, we will continue understanding these generators and these aspects of group theory. Okay, let me stop here. Thank you very much.